Welcome to a lesson on the tangential and normal components of acceleration. Acceleration can be broken down into two parts. One part is tangent to the path of motion, and the other is perpendicular to the path of motion. The tangent part or component is called the tangential component, and the perpendicular part is the normal component. The tangential component represents the acceleration of the object in a straight line, while the normal component of acceleration will increase as the speed and curvature increase. And then lastly, the tangential and normal components of acceleration will be perpendicular for circular motion at a constant rate. Let's go and take a look at a graph to visualize this. So at this point here, this red vector would be our acceleration vector. This blue vector here would be the tangent component of the acceleration vector. Notice it's pointing in the direction the object would move in a straight line from this point. And then in green here is our normal component of acceleration. So we'll be finding both the blue and the green components of acceleration in this video. So taking a look at this here, the acceleration vector valued function would be equal to the tangential component of acceleration times the unit tangent vector valued function plus the normal component of acceleration times the unit normal vector valued function. And you can see below there are several formulas to determine these components, but we're going to be using these last formulas here in this video. Notice they both require us to find the velocity vector valued function as well as the acceleration vector valued function. For the tangential components, we'll dot them and then divide by the magnitude of v. For the normal component, we'll cross v and a, then find the magnitude and divide by the magnitude of v. Remember, to determine v, we need to find r prime, and to determine a, we need to find v prime or r double prime. Let's go and take a look at our examples. We want to determine the tangential and normal components of acceleration when t is equal to 2 for this vector valued function. So let's go ahead and start by determining the velocity vector valued function and the acceleration vector valued function. Remember, the velocity vector valued function will be the derivative of our given vector valued function, so that'll have an x component of 1 and a y component of 1/2 t. So the acceleration vector valued function is going to be equal to the vector valued function with the x component of 0 and the y component of 1/2. Notice they also both require the magnitude of the velocity vector valued function. Let's go ahead and find that now. It's going to be the square root of 1 squared, that'll be 1, plus 1/2 t squared will be 1/4 t to the second. Okay, let's go ahead and see if we can find the tangential component now. So we're going to dot v and a and then divide by the magnitude of v. And we already found the magnitude. So we'll have 1 times 0, that's going to be 0, and then 1/2 t times 1/2, that'll be 1/4 t, and then of course our denominator is going to stay the same. Now we could simplify this, but since we only need to know the value of this when t is equal to 2, we'll go ahead and sub in 2 for t now. So we'll have 1/4 times 2, that's going to be 1/2, and the denominator is going to be the square root of 1 plus 1/4 times 2 squared. Well, 2 squared is 4. 1/4 times 4 would be 1, so we'll have the square root of 2. Looks like our tangential component is going to be 1 over 2 square root 2. So here's our tangential component of acceleration at t equals 2. Now let's go ahead and determine the normal component of acceleration. So on the next slide, we'll go ahead and determine v cross with a, and then determine that magnitude, and then divide by the magnitude of v. Let's go ahead and determine v cross with a. So we'll have the first row will be ijk. The second row will be the components of v, so we'll have 1, 1/2 t, and the z component would be 0. The third row will come from a, so we'll have 0, 1/2, 0. We'll go ahead and use the cofactor expansion method to determine this. So eliminate row 1, column 1 for this first 2 by 2 determinant. So give us 1/2 t 0, 1 half, 0. Here we'll have 1, 0, 0, 0. And here we'll have 1, 1 half t, 0, 1 half. This is going to work out pretty well. Here we'll have 0 minus 0. Here we'll have 0 minus 0. And then for the z component, we're going to have 1 half minus 0. So now we determine the magnitude of this. It's going to be pretty easy to do again. It's going to be the square root of 1 half squared to the square root of 1/4. It'll be 1 half. Okay, so now we're set to determine the normal component of acceleration. Again, we have the magnitude of the cross product, that's 1 half. Our denominator is the magnitude of v, which we found on the previous screen. The square root of 1 plus 1/4 t squared. We'll go ahead and evaluate this when t is equal to 2. So again, when t is 2, this is going to be the square root of 2. Looks like we have 1 over 2 square root 2. So it looks like both our normal component and our tangential component of acceleration have the same value. If we go back to the graph, that should make sense, because if we take a look at the magnitude of these two vectors, the tangent vector and the normal vector, they look like they're the same length. And you can also visualize, if you were to take this blue vector here, move the initial point to the terminal point of the green vector, the sum of those two vectors would be the acceleration vector. Let's go and take a look at one more example. Here's the same type of problem with a different vector valued function, and we're concerned about the components of acceleration when t is equal to 1. So the velocity vector valued function is going to be 1, 3t squared, and the acceleration vector valued function is going to be 0, 6t, and the magnitude of the velocity vector valued function is going to be the square root of 1 squared, that'll be 1, plus 3t squared to the second power, that'll be 9t to the 4th. So we'll go straight to determining the tangential component. So we'll dot these and then divide by this magnitude. So v dotted with a will have 1 times 0, that's 0, and then 3t squared times 6t, that'll be 18t to the 3rd, all divided by the square root of 1 plus 9t to the 4th. So when t is equal to 1, looks like we'll have 18 all over the square root of 1 plus, that'll be 9, so the square root of 10. Now it's going to take a little more work to determine the normal component, but let's go ahead and do that on the next screen. Okay, so I've already set this up to save some time. Here's the setup for v cross with a. Again, the first row is ijk, second row is from v, and third row is from a. We're using the cofactor expansion method. Again, it's going to work out pretty well. This will be 0 minus 0 for the x component, 0 minus 0 for the y component, and the z component is going to be 6t minus 0, so we have 6t. So the magnitude of the cross product will be the square root of 6t to the second, or 36t squared, which will give us 6t. So the normal component of acceleration is going to be equal to 6t divided by the square root of 1 plus 9t to the 4th. Now we'll sub in t equals 1, we're going to have 6 all over the square root of 10. So here's our normal component, and here's our tangential component. Notice the tangent component is 3 times that of the normal component. Let's go and take a look at this graphically. In red we see the acceleration vector. Notice the tangent component of the acceleration vector is much longer than the normal component, as you see here in green. And it does look like it's 3 times longer than the normal component, which is a good indication that we did our work correctly. I hope you found this video helpful. Thank you for watching.